Yes, and this repulsive shells. So this been joint work with Henry Schumacher, who I believe currently is at the TU Chemnitz still. Martin Holmes, my PhD supervisor at the University of Bonn, and Tina Crane from the CMU, whom we also talked about last week when he talked about like nice figures. And as Alain also may notice, I have also nice figures, but I did actually not follow Jean's advice because I made these figures with Blender mostly. So I chose a bit more painful route, gives you more control and the things. Yes, and we published this work this year at the Sigma conference. So okay, let's talk about what actually is sort of the background of this work. And as I said, this was geared to a different audience. So I guess most of you know what shape space is, but still we'll go through all the slides and maybe a bit quicker. So sort of the type of shape space we're typically interested in is sort of we have a topological object, in this case, this kind of circle M, and you look at the space of configurations of this object, right? How can I realize this topological object in real space? And then you have these different kind of realizations like XX prime and X double prime. And then you realize, okay, these kind of, actually animations for this. Yeah, the spatial realizations. And then on this spatial realization, which turns out in the end to be a manifold, you want to associate different deformations of your object, different costs, right? So if you math people, you say, okay, I want to have a Riemannian manifold. And a typical question would be to say, okay, here I have two different tangent vectors that give different trajectories, this u and this v. And maybe I would want to say, okay, this u should have a higher norm in my Riemannian metric than this v because it introduces like some high frequency noise in my shape, whereas v is like a very smooth and gradual deformation. If you just turning the sphere into like slightly elongated ellipse. This is sort of the general idea and the space that I have been working on for the last 5 years by now, I think, so a long time. It's just sort of space of emergence. So the logical object I'm considering is a sphere. You might not see it, but actually all these humans are topological spheres because it's just the surface of the human. And then we have, okay, we want to put all of these on a configuration manifold. So points should be a realization of this human. And so in our case now it's not a circle, but actually our M, a geometric object underlying everything is topological surface. So it's a sphere in this case. And then we look at the space given by all emergence of this topological surface into R3 modulo rigid transformations. Right. So if I translate my object or I rotate my object, that's basically changing perspective. That's something we disregard in this setup. Like actually has explanations. And so maybe one note here. For some people that know more this kind of Michor, Mumford, etc., like line of works on space of emergence and Sobolev metrics, they would typically call this a pre-shaped space. Because here they typically would mod out in the end also representations of the surface, which we do not do in this case. Why don't we do this? Because actually when we go to computations, we can work with this space, and like how to work with representations is still more or less an open problem, I'd say. But there's approaches to how to do this. But none of them are like the perfect solution. But if you actually disregard this and actually work with emergence, like keep the structure of the immersion, then we can have nice like discretizations by triangle meshes and so on in the end. So this is why we sort of in our theoretical background write this space and not the modulo translations. Okay, so now I have my space, and I said you also want to have cost of deformations, meaning I want to have a Riemannian metric on it. And what we've been using is an elasticity-based metric. Why? Because our goal is to we want to associate a cost with different deformations. And what we want to have is that, for example, in this example of a curve, the deformation on the left, going from top to bottom, should be less expensive than the deformation on the right. Right? Because you can see in both cases the endpoints are the same. I go from a curve bend upwards to a bend downwards. And on the left, I have like a smooth Borelli transformation, just like going through like a rope. But when it's on the right-hand side, I get a lot of sort of ripples in between. It's still a valid trajectory between the two, but in our sense, it should be more expensive to get like natural motions on the space. So what we do for this is we use as crucial ingredient, say, okay, people have been working on like measuring the cost of deformations in mathematical physics, in elasticity for a long time. And we use sort of their work and build on this by incorporating a Lassy-Shell energy, which has two components. So it's a membrane energy, which is basically inflame tangential stretching and shearing. any bending energy will always measures bending, so the change of curvature of the surface. And I'm not going to go into detail how these two energies look, but sort of what you can think about is the membrane energy basically measures the change of first fundamental form of your surface, and the bending energy measures basically the change of second fundamental form of the surface, or the relative shape operator. Yes, and say here. And okay, now we have this metric, and from this metric we want to go to this elastic shell energy, and from this shell energy we want to go to a Riemannian metric on nice space. And so for this we follow what's called radius paradigm, because actually this is an elastic model, and if you have a space configuration or shape space model, this is never an elastic model, because in an elastic model you have also a spring that goes back to your initial configuration. So but we want to have something like a notion of a path. If I go different paths, they should have different energy. And this notion does not exist in elasticity, just the endpoints that matter. So what we actually want to have is what's called a viscous model in mathematical physics. So you're going to have some kind of dissipation along the trajectory. And basically the Rayleigh's paradigm is, which actually goes back to Lord Rayleigh, saying that, okay, that if I want to go from an elastic model to a viscous model, I can do a simple trick. I can just pretend I make an infinitely small step of elastic deformation and then dissipate the energy I've paid into heat. It's basically saying, okay, the cost of a small deformation, infinitesimal deformation, is really just the heat, is basically just the heat that is lost to internal friction, and internal friction is exactly what sort of elasticity gives you. And if you want to write this down into formulas, what you end up with is that you say, okay, my Riemannian metric is actually nothing but the Hessian of my elastic energy at rest configuration. And this is definite because elastic metric always, doing nothing is a global minimizer, and it gives you a nice metric. And yeah, so this basically is this notion, and then from that you can start to build Riemannian geometry distance in a second. And maybe to say here, is already the first thing what is actually geared towards emergence, right? I write down like the difference between like the cost of two different emergence, x and x tilde, and not two different shapes, because that's a different notion. Because here I already know like which point goes where, and just without two emergence of the same surface, two realizations of the same surface, or disregarding parameterization, I cannot tell you this. So this is really one formulation thing. So I would have to change the formulation here, which you can do. I think this descends to like the quotient, but we like this. Okay, now we have like the Riemannian metric, and from this now we want to go to sort of a path energy, and we want to actually tell what's an expensive path, what's a cheap path, as we said before. And so typically tasks that we have in this problem is you want to interpolate, right? So here we have two shapes, like these two hands that are live in our shape space, and I want to interpolate between them. So I want to have like a nice trajectory between them. And here I've just drawn some random trajectory between the two. As before, this is like some like maybe unnatural looking path, but it does the job. It goes from A to B. But I want to have some kind of like natural path. And what's a natural path? So we could say like one notion of having a natural path is look at the path energy, which is just the integral of the squared velocity of your curve along this curve, where the cost of the velocity is measured by the Riemannian paradigm. And metric we introduced just before, and then it turns out that minimizers of this energy have like a really nice form. They're actually geodesics, right? So it's just sort of like introducing geodesics to the back door. You typically start to talk about Riemannian manifolds. You start with the metric, and then you start with connections, and then you end up with geodesic ODE in the end that tells, okay, this is geodesic. But actually, this is a variational notion. We introduce it as minimizers of this energy. There is some caveats on how you have to be careful, because minimizers, if you talk about local minimizers or global minimizers, it's a bit, a small difference, but actually like critical points of this are geodesic, just because the other Lagrange equation of this equation is exactly geodesic ODE. So we have a notion of what's a nice path, we have geodesics, and actually what we're going to do is we of course have to sort of compute them, and if we want to compute them, we have some discretize also in time. And for this, there's a very simple time that comes from like rational time degrees in physics. That was introduced by work in where I did my PhD and for the last 12 years, obviously. So it's basically saying that a discrete geodesic is just a minimizer having a discrete path and made of steps, and then for each of these steps, you could measure the elastic energy needed to. And actually, if you go back to what I said about Rayleigh's paradigm is just saying, okay, I have this path which made of many steps, And for each of these steps, I pay the elastic energy, and this gives you back the metric. And in fact, you can show that this time discretization, if you go like k for the number of steps go to infinity, converges to the path energy, continuous path energy. Okay, now so you can use this to do like nice linear graphic stuff. So here we have two gray elephants, and then you compute a geodesic between the two, and it's like this nice, like smooth deformation between the two. It's somewhat a natural movement, or looks like a natural movement, even though like the space knows nothing about elephants, right? There's no skeleton in there, there's nothing. It's just the surface of an elephant, and still sort of because this this sort of like a notion of like moving with like a least amount of energy, somewhat very, very natural and very general. It works out very nicely in many cases. And of course, this is not only interpolation, and this is only one path. Things you can do in a Riemannian space. You can talk about like, other things, for example, exponential math, which would be extrapolating. So you continue the trajectory in this case, and then start from over. And maybe one thing to say here, of course, as I said, there's no model of an elephant in this. So if I want to continue this trajectory, you can see I'm very certain that if you continue here, you will get some unnatural deformations at some point. So there's no guarantee for this, but sort of it's more empirical position in very many cases, so it's very, very well. Yes, and so they can also talk about like averaging, talk about parallel transport on these spaces. They can basically build this time discretization, but we will not do this. We focus on mostly geodesics today. And when I said this leads to like very nice interpolations, there's like one crucial problem with the space. So here we see like a very nice geodesic on the space. This is a geodesic between these two end shapes, but somewhat doesn't look natural, right? So you wouldn't do this kind of motion in real life. It would be very, very painful. This is because you have elasticity in there, and elasticity only comes like local regularity of surface. There's no notion of like global intersection freeness. And sort of the leading question for this project has been sort of how can we modify our tape space, how can we augment it to guarantee that along geodesics we have self-avoided surfaces. Because that's something natural to ask for in many cases, right? For example, here we'd like to go maybe on the outside or do something, but not to the back and out the front. Unless you're modeling a ghost, then of course it might be a valid approach. But it's so okay. Let's talk about this sort of thing. So that's the main thing we want to achieve, and that's what we want to talk about for the main purpose talk. And as I said, elasticity is not enough. Elasticity does not model global intersections, so we need something more. We need another ingredient to our shape space to make this work. And again, we turned here to work from mathematical, map theory actually, and geometric energies and geometric relational problems. We just actually look at repulsive energies. I know this is a point where you see that this was geared towards another audience, because this is like a very definition of words, but actually I kept just the spirit. So what's a repulsive energy? A repulsive energy is saying, okay, I have an energy on my surface and I have surface configuration on my immersion, and it's called repulsive if this energy explodes, meaning it goes to infinity, if my surface approaches self-intersection. And crucially, this also implies that if my surface is self-intersecting, then this energy is infinite. But note it's a bit more because actually you have this like ramping up, and it's not just suddenly infinite, it grows there. And okay, what kind of energy can we use for this? And the particular energy that we've been using is the tangent point energy, which has been produced by Bach and Orloff in 1995 for Kurz originally, and extended by other people to surfaces or believing arbitrary dimensional submanifolds. And basically you have this double integral, and for each pair of points on my surface or a curve or whatever, I look at the so-called tangent point radius, which is R here. And the tangent point radius is the radius of the small sphere that's tangent to one point and goes to another point. For example, here you see this gray circle as tangent at X and passes through Y, and the reciprocal of the smallest radius is this R, all goes into this integral. And so then we have some exponent also, which basically is some integrability exponent. And the very nice thing about this is actually repulsive if we make alpha big enough. So for surface alpha bigger than 4, this is repulsive. I think course is bigger than 2. And this is basically because now if you can imagine that if your surface approaches self-intersection, people would be like, let's say this X and this point get close, then the radius between them will get very, the sphere between them will get very, very small. The radius will get very, very small. And so one of the radius will go to infinity. And sort of a crucial observation you have to make is, okay, I can tell now this works, but this is of course not obvious, right? Because you have some kind of like, it has to go fast enough to infinity that actually if you go to intersection, it actually goes to infinite everywhere. Like in a, if it's just one pair of points, let's take a zero set, so whatever happens there, we don't care. You have to show that it actually works in general. And at the same time, you have to show that it's not too fast, right? Because one thing you might say, okay, I do repulsive energy, let's say I take the Dirichlet energy, like 1 over a distance on my surface between pair of points. But you cannot do like repulsive energy on surfaces because you can choose the exponent if you're 1 over distance, and either it's like too weak, it allows surface sections, or it's too strong that it's always infinite, even if your surface is not intersecting, just because like you've always like points that are close to each other. Right, so like the distance, there's always pairs of points with a small distance, and you have to fix this. And here is because you take this radius. So if you have 2 points that are very close to each other, they have the same tangent vector, then it's ready to become like very, very big. Because it's supposed to be tangent at the one point and go to the other point, so it becomes like more or less equal to so it has to be more or less straight between 2 points. And then this reciprocal becomes like very small. So only if you have points that are far on the surface, but close in ambient space, this thing will blow up. And I say this again about Borelli, but it's like a huge work, people starting in 1995 that has been like investing in its energy in like mostly mathematical knot theory, because it comes from mathematical knot theory, but can show that if you have different homotopy classes, they are guarded by infinite energy walls on this energy, and that's where this came out. And then people have been working on this for a long time to like study its regularity. So what kind of like space does it live on? Because actually this is a thing that naturally lives on fractional superspaces spaces. So finite energy does not just give you that your surface is non-intersecting, but also guarantees you a certain like fractional superspace regularity, which is for some people like very nice. If you want to do actual work with this, can be very painful because it also means like fractional superspace means non-local. And it's obviously non-local, but all the like differential structures non-local. And recently, like what Tina and Harry have been doing together with some PhD students, they've been looking at actually being able to efficiently compute this numerically, and if you do efficiently like gradient descent, like efficient optimization of the energy numerically, which I said is painful because it's fractional structure and it's non-local structure and so on. But sort of we didn't really have to do this. We could just build on this, and like now we want to incorporate this energy into our data space. Okay, so let's talk first about the NEAT approach. Yes.
And to be clear, because you're not going to dive into it, but if you just discretize your shape as point clouds, probably it's not good enough because due to discretization artifacts, you could have self-intersection when a point passes through. So you have to be super careful.
Yes, you have to also be careful if you have a triangle mesh, how you do quadrature. Because we'll see it's not straightforward, and we'll actually see that this can be an issue. Right, so let's talk about how to build this into our shape space calculus. So as I said before, we have a path energy, and we just optimize the path energy. That's what we effectively do to get like GD6. I could just say, okay, just add this potential over time, and integrate it over time, and this will do the job in some sense because it will prevent self-intersections, which become infinite if you have like for a significant amount of time like self-intersections on your path. But this has some like unwanted consequences. So here's like a minimizer of this energy between like these two human poses that we've seen before, and what you get in the middle looks more like a gingerbread man than like an actual human. Just because if you minimize this energy, you have a notion to like this energy smaller tangent point energy, right? So you get more effects than you might like to have. For example, this you have close points on this human, right? You have these toes down here. So here the tangent point energy will be very big. And you would like to remain very big if you interpolate between the 2 points, which is not given if you just integrate the potential. So this then leads to these blowing up effects. You kind of start to play a game and like make the factor in front of this energy like very, very small. And if you make it small enough, then it might work. But the problem is, if you make it small enough, it becomes like a barrier term. And like optimization with barrier terms can be very, very hard, especially if you make this factor very small, because then like a small change in your position will lead to like a huge blow up in energy. And so this makes them very like painful. And for those reasons, it's not what we want to do. We have to have a different approach that works better. And the project we came up with is a graph manifold approach that we look at the graph of this energy over basic shape space. That basically means we embed our shape space in like one dimension higher, one ambient dimension higher. And then we can say, okay, we want to use in the one dimension higher, we want to use a product linear metric. Where in this old dimensions, I just use my original metric I had before. In this new dimension, I just use the Euclidean metric. And the idea is that if I have a point where this energy is infinite, this would go like infinitely far to this top. Like you see these peaks basically where we have some self-intersecting shape. And so the idea is, okay, if I take this metric, then I would have to go up the peak. It becomes like very expensive. Yes.
Sorry, what is phi?
Sorry, phi is the tangent point energy in this case, or repulsive energy.
Okay, so
from before. Yeah, big phi will always be the tangent point energy. You can say it doesn't have to be tangent point energy. There's like other things like Möbius energy. You know, there's like a whole zoo of like non-local energies you could take that are repulsive and so on. But we just, because like Keenan and Henrik wrote on this before, we like the tangent point energy. We have the knowledge and expertise in that.
But so why does this prevent the bad effect you had before?
Okay, that's
How
good.
do you really?
Yes, it's a very good question because basically now my metric I have my new metric is this purple thing. It's given my original metric, and then sort of if I pull it back to my base shape space, it's a local change in potential. Right, so I get the differential of my potential squared. Basically gives me like a rank 1 update of my metric. So basically this dx of phi is linear operator on my tangent space, and I put a u in there. And in fact, this is just matrix, like a vector that multiplies with another vector. And the first crucial observation is this actually works. So if I have a shape that has like infinite energy, then the distance to the shape will also be infinite. And especially if I move toward this, my distance will blow up. So actually I prevent like self-intersections if I compute geodesics, because then I have like finite distance. And this is actually sort of by Gordon in the, I think, 50s. So basically you can show that actually under some assumptions, like a 5-dimensional manifold, which is at least three regular, then if you want to have a Riemannian metric that is complete, geodesically complete, then you can show that it always has this form, like some other metric plus some of this one function, where this function has to fulfill certain properties. This doesn't really apply in our case because it only works for finite dimensional manifolds. The proof, at least, how it's known today. And in the discrete case, we'll see later, it's unclear on our function, definitely not in the way we write down fulfill this criteria, but it still sort of gives you motivation, like from a mathematical perspective, why you should do this method. And if you look at the path function next, you will see actually why this prevents the effect that we've seen before. Because, okay, now you can start again. Okay, you want to have a path energy, you can just write it down. It's just integrating this Riemannian term. And this new path energy has like the old component on the left, and then the new component, which is just integration of this derivative of the potential over time. And this is something very concrete again if you look at the discrete energy. Because, okay, we said for the first part, we just approximated like stepwise by the summing up of elastic energy. And if you now do like midpoint quadrature or whatever you want to do for the second integral, for this discrete set of paths, we see what we end up with is just the square difference between potential between like neighboring points. So basically, if you have two shapes that have the same amount of tangent point energy in the beginning and the end, then you have an incentive to keep the same amount of tangent point energy all along the trajectory. For example, in the case before, where this human, where you say they have like very high tangent point energy, just because there's like this foot where it's like very close to intersecting, you want to have the same level of tangent point energy along the trajectory. And actually, it turns out, for example, in this human example, this looks like very nice. So you have in green again the relation from before, and now in blue in the front, what we sort of get out of this modified path energy. Yes, and you can see that you get like a nice movement that goes from the back to the front around the body, and it prevents self-intersections along the way all the time, and it does not blow up, but it keeps sort of a similar level of tangent point energy along the trajectory. Of course, if you have like different levels of tangent point energy in the beginning and the end, it will change. But in this particular scenario, it's more or less the same in the beginning and the end, and so it stays the same for most trajectory.
And also a question is that you said that, for instance, in those shapes at rest, actually overwhelmingly the tangent point energy comes from the toes.
Yes.
So you could imagine, intuitively that maybe in this energy, it's like the main order of magnitude actually comes from the toes.
Yes.
And so the energy does not really see what happens elsewhere. Like you could imagine something like that, because you have a
Yes,
term which is
okay.
on the order 1000. And so if you have this big term, everything else does not really matter as far as the energy is concerned, but you never see anything like that happening in your...
Okay, so I mean, we kind of see this because like optimization of this is like very, very hard. It's not, it's not an easy problem. You're not in energy and you have all kinds of things. There's some things to make it nicer. And for example, one thing that I omitted here is, of course, right now I just write phi and I sum them together, but actually the elastic energy and the tangible energy are typically on completely different scales. So
What?
they are completely different scales. So I have to rescale, I have to put some weighting factor in there, which comes against from this fact, because if I just put this in, then nothing else matters anymore. So I actually have to scale, typically I scale this this tangible energy by something between like 10 to the minus 4 and 10 to the minus 8 to like become on a similar level of energy. And yes, you might say, okay, maybe we just ignore like some parts that we actually matter about, but in fact this was not that problem. Yes, okay, so this is basically sort of the model that we have, right? So this is the pattern you have in the end, and as I said before, the nice thing that we did it this way also is to not just add like the penalty term to things, you can just do everything we've done before exactly the same. We can get an exponential map, we can get power transport if you want, we can averaging if you want. That's basically all the sort of theory and all the machinery that we've been through before applies the same. Except for some big difference, if you come to actually realizing this in a computer, you want to actually implement this, everything gets much harder now that we have the tangent point energy. So so far we've discretized in time, but we always kept like continuous surfaces. Now the next step is to like actually discretize this in space to be able to implement it. And discretizing in space in my case just means okay, we go to a triangle mesh, right? So it's nice to write all this down. Continuous surfaces makes notation nice, but then we work on triangle meshes. And for a triangle mesh, we look at piecewise affine immersions of our mesh to the real surface, to real space. So triangles like that. And then this is our configuration space, like our immersion space. And here it is equivalent to like having nodal positions for all vertices in the end. That's really the vector you work with in the optimization. And here's then the thing, as I said before, if you would now have to mod out renormalizations, so sort of it's not really clear anymore what this really is. Basically, it amounts up to like remeshing and really having like correspondence between like different meshes and these kind of problems, where of course there's like a lot of work on, but I don't think anything really is an fashion that works nicely with the setup and gives you like satisfying results very right now. Okay, so we have triangle meshes. We need to discretize our elastic energy from before. This is work has been done, as you can see, over the last 20 years, or even more in graphics mostly. So we use the graphics approach to basically discretize the phenomena that comes from energy and use like a discrete equivalent. So for the memory energy, we just have to look at the change of shape of particular pairs of triangles. So what's the realization T and T prime of one particular triangle? How does it change? How does the area length so on change? And then for the bending energy, we look at dihedral angles. So we have two neighboring triangles and there's an angle between them. And then we basically just look how this angle changes between these two configurations. So it's really a square difference, appropriately weighted to get a nice integration in the end. And this is, yes, and this is like, we can show that in a certain assumptions that gives you like also like a converging approximation of this. But there's some caveats here again, because you have to have nice mesh quality and so on to actually for this to hold. Okay, so this is now basically what is the old thing, like of that you need to make this this shape space happen with just the elastic n metric. But now to actually go to like make this non-level thing work, there's like a lot more ingredients you need. So we need a multiple approximation. We'll talk about in a second. Basically to make everything fast enough. We need a depth of refinement of our mesh of the depth curvature. Prevent exactly the problem Jean mentioned, that if you have like a coarse mesh, you might have intersections that don't see but coarse curvature. Then two more things that basically just like tricks to make everything more efficient, where you do the proper refinement, so you start with a path that's just a few time steps, and then you add time steps. Just have that nice acceleration for the things that are finite, finite results in time. I mean, one thing, everything that you see today basically has at least 512 time steps, because everything that you can see today is basically geared towards you can show it nicely in 60 FPS. So they did a nice smooth information. But we start with the 8 time steps, and then you refine by the power of 2 or that. And the other thing we do is spatial prolongation. So if you do this in a very defined resolved mesh, of course, it's something very, very expensive. So we try to capture the most important phenomena in a coarse mesh, as seen here. And this typically works very well for this information that we see, because you care about the overall deformation, and a lot of it just stays the same. And because again, it goes back to if you have a coarse mesh, you need to actually care about the curvature. A very defined mesh, you don't have to, but if you have a very coarse thing, you do. And then in the end, we plug all of this together in trust region-based optimization. So you have actually a trust region Newton scheme with a CG solver. I have CG solver for the trust region subproblem, where then you have to do some appropriate preconditioning and so on. So as you see, this is basically what I've shown you so far. It took about, let's say, a month or a month and a half to realize and to write it down. And then this took another year and a half to actually make this work as well as we see it right now. And so yeah, I'm gonna focus on these two things because these are just generic concepts, but these two first things actually somewhat specific to this energy that you see here. So okay, this basically revolves all around the tangent point energy. So how does we visualize tangent point energy? So remember from before, the tangent point energy has this double integral form of this 1 over tangent point radius between pairs of points to the power of alpha. And then the first thing you can do is just do midpoint quadrature. Right? So you have a triangle mesh, do a midpoint quadrature. You can double sum over all triangles, including the neighboring ones, because for the neighboring ones this will always be infinite, and the neighboring ones is the same one because if 2 points are the same, then this will be infinite. And then you get basically this k. I didn't write this, sorry. So this k is just 1 over r between these 2 points. And basically you get the 1 over r between the 2 centroids of your triangles waved by the area. So this is basically straightforward midpoint quadrature. The first thing maybe you learn if you talk about infinite endowments or whatever. The problem with this, and this is okay, but the first problem with this is there's 2 problems. The first problem is this is very expensive, right? Because this is number of triangles squared. You have to sum here, and for the energy, okay, that's still fine, but if you want gradients and so on, it becomes very expensive. And what we do here is do a multiple approximation, which is basically a realization that if you can speed up basically computational energy, because there's a lot of pairs that actually don't measure for this, right? So if a triangle pair that's very far away in ambient space, the energy contribution will be negligible. Which basically goes back to what you just mentioned, John, right? So if there's maybe some contributions that you don't see at all, and actually it's true because we even ignore them in the optimization. And then of course, okay, multiple, we have certain acceptance criterion, which is basically saying, okay, if I have 2 triangles, I look at their size, and if the distance between these 2 triangles, or the distance between their centroids, is big in relation to their size, or big, some factor you have to specify, then you just ignore the contribution. Or more concretely, you take a big patch of triangles and just consider them as one contribution. Right, so basically you sort of say, okay, I divide my whole surface maybe in 2 parts, and then of course they will be close, but you start to subdivide, and until some point you realize, okay, I have parts that are far away, they maybe consist of 100 triangles each, and I can just pretend they're one triangle with one barycenter, and this gives me a somewhat accurate approximation. And then this allows you in the end to compute the energy not in O of n squared, but O of n log n. I mean, of course, the approximation goes also a long way back to 70s, I think. And it comes from particle physics. There's an Wolfram-Parent algorithm. And as I said, there's this factor where you control basically the trade-off between the how far your lines have to be away to actually consider it irrelevant. And this factor gives you a trade-off between speed and accuracy in your approximation that you can also play with in your actual algorithm. Yeah, you can see, okay, how much can I push it? We still get nice results and be fast. And actually, this turns out that if you do this and implement this nicely, using C++ or whatever, so maybe also difference to like last week. I do all of this was done in C++, and I do a lot of Slovak still in C++ and not in Python. Yes, if I put this nicely, actually the cost of this is manageable. By manageable, I mean it's not that much more expensive than elastic energy, which is sort of the baseline. If it's because it's the baseline cost you have to pay anyway for this method. So it's of course more expensive, and so the implementation more tricky. But the cost of the energy itself is not that bad in the end. But there's another problem is this triangle, this midpoint furniture can actually miss intersections, right? So if I have two triangles that intersect away from the centroids, the energy is perfectly fine. It's finite and it doesn't care, right? If I have a coarse triangle mesh, this can actually happen. So here, this is actually observation result from one of the geodesics. If I don't use adaptive predator on this like somewhat coarse mesh, and I can get actually like severe intersection, it starts to tunnel into configurations where like a lot of triangles are intersecting and it's just locked there. And that's basically because it does not blow actually up due to this midpoint curvature. And our solution for this problem has been to look at a multiple phase refinement, which is basically saying, okay, if I have two triangles, but my multiple says, okay, they're close enough so that I actually have to compute this pair of triangle as an actual summand in my energy. Then I do one more thing. I look how close are they actually, and if they're too close, then I start to refine them and subdivide them into 4 triangles. This all happens virtually, but that's the idea that you have. You split 4 triangles, and for each of these now 16 pairs that you get out of this, you look again, are they far enough away from each other so that I can just sum them together, or do I continue refining? And so basically, for this, use the same multiple condition from before. You can relax it a bit, so you can because just wanted that if it's like infinitely close, that it blows up. But yeah, you do this and repeat the process. And for example, for here, for these 2 triangles, you can see that where they collide on the tips. You can see that here it starts to refine more and more and more, and then you get these small blue squares. Where actually you can see you have the subdivisions just at the tip where they meet. And in theory, we repeat this process to infinite depth of our refinement tree, and then this actually will sort of prevent intersections except in some generated situations. But of course, in practice, you do not do this. In practice, you have to limit your tree depth, otherwise it becomes too expensive again. And sort of that's what we do. And then if you do this, then we realize that actually the cost that you pay for this is not that bad. So actually, there's just a small amount of strength where this actually happens. Of course, if you create some examples, we'll see some where you have like a lot, you have a very strong area of intersection, like where a lot of the surface is close to yourself, then it's become very, very expensive. But for many examples, for example, this human, it just actually matters about like the tip of your fingers, and maybe it's sort of like some things like the toes and so on. But like the area which actually refines is like very small, so the additional cost you pay is manageable in the end. Yes, and with this, basically, you have all the tools now applied to finally look at some like nice images and some nice examples that you can create with this method. And basically, we will see 4 categories of examples. So we will see interpolation, which is what I've told you about all the time. We'll also talk about extrapolation, where I actually haven't showed you how to completely do this, but we can build it on top of this. Then we'll see an averaging example. Again, you basically generalize this to get like weighted averages of shapes. And then you get some bonus examples that sort of are not really shape-space examples, but still like other fun stuff you can do with the elastic energy and the tangent point energy. So let's start with interpolation. So you've seen the human examples. Here's another example of 2 human hands. Basically, take one mesh, but 2 components, and goes from like this. Like, it has like an excellent vibe to it. And this like a very, for me, this is like a very, very interesting example, because when we start a project, this example, we said we would like to do this. And in the beginning of the project, I said, no way in hell we're going to be able to do this. Because you see, it's like very tightly interlocked. There's a lot of contact, almost contact along the whole path, right? So it's changing, it's like sliding for a long area along the way and going back in. And but still in the end, it works out very nicely. One caveat, what you have to do is you have to somehow give it some idea. So if you initialize the trajectory, you do a configuration like this, and then it can move back in. But basically, yes. And for this, for example, maybe a small thing to explain about this, like how this comes out But how to get to this example, I bought a rigged hand for a blender. So I rigged basically some skeleton model for the hand. And then I started to like modify it, like actually move it close together. And like manually, like with like painstaking labor, I learned Blender and how to rigs and so on, and I moved it close together. And then really I realized I'm not good enough at it. So we still cannot do actually like really close. I cannot get it like really closely, look nicely, and not intersect with this rig model. So what I did is I did just a small like starting configuration, and then I used an exponential method to make it really close. And I did both configurations, and so then I could do duties between the two. So actually, I use our own tools as modeling tools to get this example, which is very cool as well. You can also include other terms in this into this energy, not just the tangent point energy itself, because we can play the same game of modifying this with arbitrary potentials. And here's one potential that's like basically a tangent point energy, not between the shape and itself, but between the shape and some object, some obstacle they want to avoid. For example, here you just turn a tube, you see a sphere that goes through this object, and you can also then start modifying material parameters. So on the right, you have very soft material, which means that bending is very cheap. Whereas soft is actually here in this case like very thin, so bending is very cheap. And on the right, you have a material bending is very expensive. You have some great deformations. And one thing to notice here is that this is also like very tricky because these like configurations, these like buckling phenomena in elasticity are very unstable, right? So if you stop your position just a bit early, to say, okay, I'm fine with a gradient of 10 to the minus 5 until 10 to the minus 6, and it's completely different, which is like very interesting because this sort of interaction creates some like very unstable phenomena. You can also apply our method to like practical real-world problems. So if you have to turn your clothes inside out or back, you can do this now. It's a method with like nice manipulation between two configurations. They are guaranteed intersection-free, so tells you how to do your laundry in the morning if you forgot to do it after you wash your clothes. And it's like and really at this point to say this bending, for example, is not with Blender, but I think I don't know who like to create this blendering because he's a very career graphics person and that's a very fun thing. And he actually for this glove he manually wrote a new shaker, just like a knitted appearance to this thing, which you can, if you want to learn about how it does this, go to GitHub to do it. Yes, okay, so that's what was it for interpolation. Next thing is extrapolation. And one thing you can nicely do is you can start to look at how to fill a leaf. So this is like very similar to what I told you about what I did with the hand. Basically, you just prescribe a small initial deformation, which is so small you can't really see it here. You almost can see it because just like the tip is slightly going up. And then you can continue this, so going up in an extrapolation. And you really see is that basically the voice section to do this, it starts to nicely curl up inside of the object itself. And it will also sort of curl up if you just do this with the elastic exponential map, but it will completely self-intersecting, right? So there's no reason why it wouldn't. So just the chip goes through, and just in the end, it's just a big mess. But here we get really this nice curled up motion in the end. Which is another example where I say, "Oh, if that's going to work, I don't know." Actually,
Excuse me, what did you say was a big mess? I didn't.
if you just do the extrapolation without the tangential energy, just an elastic shape space, it's just it just rolls up to itself. It's just complete one intersecting tube in the end. So if you come to averaging, we have then you can look at like Fréchet means on the shape space, and if you do this on an elastic shelf space, then you have some like certain configurations and Judaism again, you get a lot of like self-intersecting all over the place on these weighted average between these extremal shapes, x1, x2, x3. And then you can switch over to like repulsive shape space, and you get like guaranteed means of free of softness section. Which like a thing that's beyond the interpolation, extrapolation things you can do on the shape space. Okay, then let's come to the bonus part. So as I said, there's no stuff that does not need the shape space machinery. It's basically just you add together tangential energy, elastic energy, and you see what kind of fun things you can do. And one thing you can talk about is isometric embeddings. So that means actually I prescribe a metric on my surface, and I want to actually find an embedding, not immersion, but an embedding with this given metric. This might not be possible, but this is something you can do. And basically in the elastic case, this means okay, I minimize bending energy because I want like a minimized bending configuration. I add tangent point energy, so minimize tangent point energy because it's not intersect. And furthermore, I add as a constraint as a very strong penalty term the membrane energy to a prescribed metric, which is given as length or something. And one example we can do is here is the hyperbolic disk. Of course, we can go to the infinitely wide Borelli disk embedded, but here it's a subpart of the hyperbolic disk, and you get this like nicely curly shape out of it, which is intersection free. And if you do the same with just elastic, you get self-intersections. Looks still nice, but it's self-intersections. Furthermore, if you look at flat torus, I guess many of you know sort of you have your project rendering of this flat torus. When we talked about this last week, right? So which actually like a real rendering of the convex integration version of the flat torus. And here you see one which is not actually isometric but close to isometric. And if you further go to the right, you get more isometric gas, because you increase the penalty weight on your energy. And you see that more and more like wrinkles start to appear. Like a similar phenomenon starts to appear like inside, which I don't know, it's a very cool example. Then you can start to add additional constraints. For example, here we will pack an octopus into a box, which is by saying, okay, I want to minimize the elastic energy to initial configuration. It should be intersection free, and I put a box constraint like a shrinking box that also should stay inside of there. And then you can nicely pack your octopus into like a very, very small cube. So if you have now ship it around the world, it's like very cheap. Yes, and I can guarantee you no octopus was harmed in creating this figure. Of course, it's obviously a toy.
And so what happens next if you continue?
Yeah, so at some point, basically, it's kind of stuck because you cannot compress it. I mean, you can completely destroy the structure of it, and this will happen at some point. That basically the arms will just start to collapse and become flatter. Yeah, and also the optimization becomes more expensive because right now you see this octopus is almost in self-contact everywhere, right? So this adaptive refinement becomes much more expensive to compute. You can do a bit further, but at some point also that might break down, I guess. And then for the final problem, we have a very, very old problem, which goes back actually to the Bible. So maybe in the Bible it says it's easier for a camel to go through the eye of the needle than for a rich man to enter into the kingdom of God. And this, of course, has sparked a lot of research from financed by rich people, basically two directions. So there's a lot of longevity research, as you might know, which is basically saying, okay, if I can't get into the kingdom of God and cannot get into heaven, maybe I just don't die. Like one solution. And of course, there's the other solution, which is asking, can we actually make a camel walk through the eye of a needle? Which is, of course, a big research question. And so we have some preliminary results on this in this example, where we can at least make our camel through the eye of a needle. If this now fulfills the definition of walking, this is maybe it's looking for future work.
It's a big needle.
Well, yes, it's also a big needle flight, yeah. Also a big flight. Yes, and with that, thank you for your attention. As Dean showed you today, a mix of what we've done before for the shell setup with shape spaces and the tangent point energy to the end gives very, very nice interpolations and very nice animations through the shape space capsules. Thank you.
So if you have additional constraints you're going to have, it's essentially you add them to the potential energy and then you modify the matrix and okay.
Yes, basically, for example, for this obstacle example,
Yeah.
I have just two potentials. One is the tangent point energy potential to itself, and one is basically the tangent point energy, right? One of the integrals actually of another surface, and that's also a potential average. So basically, this framework applies to a lot of things.
I'm not quite sure I understood something. If you, in the last function, in the geodesic, let's say, you tend to favor constant tangent energy because you more or less penalize the gradient. I don't get why you don't need to have a scheduling on the reweighting of this part of the regularization. Because let's say you have someone with arms crossed and just a T-pose, the tangent energy is going to be way different.
Yes.
So why does it work?
Okay. So what I said, this comment where it stays focused, it favors constant tangent point energy, It's only true if for the two endpoint configuration is the same. For example, your example, it's like very different between the two, right? And there I would actually want to have like a linear interpolation between these two values of tangent point energy. So it would like decreasing tangent point energy along the trajectory. But this really depends on the endpoints of configuration. If the energy is the same, it should remain the same for the trajectory. If it's similar, you would like to have somewhat like a linear interpolation between the two, just because it's like a quadratic energy of like consecutive steps.
So do you need to add manually a scheduling of the weight of this part of the metric or not? Or
No, okay, so what you need to know, and it happens automatically in this scenario, what you need to do, as I said before, you need to like rebate it to like actually work nicely with your like elastic energy, like mostly numerically. I mean, in theory, it doesn't change the behavior, but and elastically, if you actually work in numerics, you need this. But yeah, no, you don't need to adapt this extra examples. It's mostly you need to adapt it to like the type of mesh and like the structure. But for the human, like, it's like this motion or this motion parameters would be basically the same.
I had a question about the discrete tangent point energy.
Yeah.
Is it like when you, for example, when you subdivide the mesh or when you change the mesh topology, does it stay the same? Is it the reason why you divide it by the area of the triangles?
Okay. So I don't think there is a formal or rigorous proof of convergence. I know that Henrik has been working on some things and has made some progress and can prove some things on convergence. And I'm fairly certain that at least for this tangent point, this midpoint approximation, if you just refine your mesh and mesh everywhere, it should work. And we're somewhat confident that the multiple approximations also works, and the adaptive energy not lying here actually. But also it's not really like better approximating the underlying continuous surface, so they just add project points on flat triangles. It's really more like discrete state. So it doesn't really help with the convergence to the continuous object. It's just more like a numerical trick almost to get for the discrete object that you have like an accurate solution. Yeah, but we don't have any rigorous proofs for that yet.
Okay. Yeah, so if I can ask you, I think that obviously it's all of your work on this is very impressive, especially the numerics part. But realistically, very, very few people are going to be able to implement that. I mean, it took you a lot of time, etc. And I'm just interested because, for me, if I had been in your shoes, after 2 months of, okay, it's a good idea, and then realizing that computing the real quadrature was going to be way too much effort, I would have tried to find a shortcut, being inspired by this tangent point energy, because if you have two triangles, maybe you can have a closed formula that gives you the distance, and then, you kind of handcraft something which is good enough and that you can implement, using Cheops or just a basic double sum, but you didn't do it. So I'm just wondering, is it just because you wanted to do the hardcore subdivision thing, or it's really impossible to get something which is satisfying?
So as before, I mean, I do my figures with blenders, so I obviously like paint. No, that's a lie. Actually, doing figures with blenders is very easy, but it's. I think the answer is twofold. So the first thing is we tried to find a formula for a closed form formula for two triangles for this, and we didn't, because otherwise this would have like sort of made this whole like that depth pressure point unnecessary, because you could actually on a triangle level have an exact formula. So for this multiple approximation, you might just get away with like a very smart computational schema, like a GPU or something, but still. The one thing we're doing is I'm talking about like small resolution meshes, like say 1,000 vertices, and I'm somewhat doubtful that actually get like a good enough speed up with even a clever implementation of the double sum to a GPU to beat this method here. And then the other part of the answer is also that I did not implement actually this multiple approximation. I mean, I did in the end, but in the beginning, this comes from the work from Henrik and Keenan before. So they have a very lot of expertise in implementing this, and it works very well. So we run with it. And so the pain for me really was like making the numerical optimization work. This trust region method and so on. And so maybe if you maybe I didn't say this before because it's actually something that's from this week or last week. So now there's code available. So what you want to do is just solve. I did not link it because I said just copied the slides, but then on GitHub you can find the code for this for the shape space part and also for the tangent point energy implemented in C++. Sorry, there's no Python interface. I hope it's easy enough to if you don't want to compile.
But just as a follow-up for the, because I thought also about this closed formula for two triangles. But you could, even if you don't have the formula, you can tabulate it or like, or do you see what I mean? Like,
Basically,
or even
Like it's like doing the subdivision. It seems really painful. So if you can take any shortcut, it's good enough.
okay, so actually it's sort of from, I mean, from an implementation point of view. So implementation point of view, of course, you have to be careful if you do the subdivision, because you cannot do it actually, you have to do it like virtually, you can actually construct these kind of things in memory. Then it's like painfully slow. If you have to, allocate memory for all these additional points and so on, what you just do is you iterate over them and you move the points in a clever scheme, which Henry came up with, which is like very good. And then coming up with that and having the derivative is not that bad. Because once you have actually implemented this multiple structure, it's like super similar in spirit. So heading is not too bad. So actually, so what I did is I can say this because we wrote a paper and wrote kind of things in there, and pseudocode in there. And and at some point I were like, is this actually like enough to implement this? And what I did is I set out and implement this myself again using C++, having never implemented this engine before, because we just use Henry code. And it was was a nice project. It was took me a couple of days, but it was completely okay. So even with this like subdividing thing, so I think it's actually once you know how to do it, it's not too painful anymore.
just one last question. Have you tried to, what happens if you drop the ball on the plane? Does it bounce?
That's a very good example. No, it does not bounce. Because this is actually okay. So if we have this example actually, we have computed this at least with some like approximation of this energy, and you can find if you look at the Keen's talk about the CHS in there, because basically what you accept from like physics, basically if you start with the ball up here and you extrapolate like the movement downwards, it will go to the ground and go back up again. But for us, it's different. As I said, so if you want our tension point to behave somewhat linearly, right? So if you get closer, the tension point energy will grow. And you want it to grow. And basically what happens is, you can also think about this if you see this graph on the full picture. So basically what it's saying is like the ball dropping to the ground is basically straight shooting up one of these speeds.
Sorry,
It's basically shooting up at the exponential map, like straight up one of these peaks, and exactly onto the peaks. And what will happen is it will just go up, but just the movement will get slower and slower and slower and slower and slower. Because the tension point energy gets bigger and bigger and bigger. Basically, so what happens is your ball, it never touches the ground.
yeah, no, okay, but if you don't shoot exactly to the peak, but
Okay,
slightly off, then it will go back, and so it might bounce. So basically, if you don't drop exactly vertically, but slightly, oh no, I don't know. I'm just.
I don't know. Okay, for this example, I'm not too sure what happens with the ball. So what happens in general is you can have. You're right. If I don't shoot up exactly, then we'll do something different, right? If I shoot too far off, it will just go around.
Yeah.
What I can show, you have some like nice examples with just like points. We actually plotted this how what happens and if you just shoot like slightly off the middle, what happens? You spiral up to your peak. So it basically would go. It's actually landing in the landscape. It would like spiral up the peak, and this can be like some spiral moving for points, for example. And actually, I don't know what happens with the ball in this case. That's actually a very interesting question for having. Okay, I don't know. Maybe it was still
Because I have seen works in there have been works to model particle interactions seen as small balls like colliding, and basically they had similar models like repulsive models for interactions, and it was really a model for how do you call it, collisions for, yeah, for, so I don't, it looks like it could work.
It's actually, we also have, our paper, we have like at the beginning, a big section about like points. We just do exactly this, just for like point pairs and point collection of point models, just because it's like easy to introduce like the shape space idea and what this kind of means. And there we also have examples like this, where basically they shoot points to each other, and but I'm not. And actually, there you get this kind of like spiral movement. I think what happens is the front goes around, and it starts to spiral. The other point gets closer and closer and closer. But yeah, if you look at this, maybe I think it's very similar, because there we don't use like tangent point energy, just Coulomb energy.
Okay. And maybe a remark is that when you present the subdivision scheme, you present two triangles that intersect. But I assume that in practice, it never occurs. Like basically, if they intersect, your energy is plus infinity, so you know that it's scrap. So
Yeah.
actually, in practice, it's just always triangles that may be close together, but
You always, we put the distance between these triangles, and when we see the distance is 0, so it's intersecting, we immediately return infinity for energy. We don't care anymore, whatever. It should not be here. So basically, this deck, you immediately make a step size smaller. Your just region smaller.